Well, this is math. 424, PDE, 7th class. That's where we are today. And we're learning a little bit about ordinary differential equations, which is a prerequisite to dealing with partial differential equations. There was some homework that was due last Wednesday and another homework that's due this coming Wednesday. Any questions about homework problems or any other problems that you've seen so far?
Professor, can you go over question 6 from page 311 to 312?
I will try. Page 311. Which number?
Number 6.
So find all solutions of y prime sine x plus y cosine x equals 1 on the open interval from 0 to pi. And the first thing to notice, which is very important, is that from 0 to pi, sine of x is not 0 for x in the interval from 0 to pi. And it's important because we like our first order equations to be y prime with nothing multiplying it except 1. So we would like to divide by sine x. So divide by sine x, we get y prime plus y cosine x over sine x equals 1 over sine x. Or if you like, y prime, well, let's just leave it like that. So what is our standard notation for writing a first order non-homogeneous equation? So y prime plus p of xy equals q of x. So our p of x is cosine x over sine x, or cotangent of x. And our q of x is 1 over sine x, which is cosecant of x. So let me just check one thing. Yes. So when we have our first order equation written in this form, right, we define a of x to be the integral from some a to x of p of t dt. And our general solution is f of x equals b e to the minus a of x. plus e to the minus a of x, an integral from a to x of q of t, e to the minus a of t dt. Right? So what are the different functions that are involved? A of x is the integral from some point a to x. What is p of t? P of t is cosine x over sine t, cosine t over sine t dt. If we make the substitution, let's say u equals sine t, so du is cosine t dt. This becomes the integral of dt over t, sorry, du over u, which is log u, which is the log of sine of x. Okay. All right, any questions about what's going on?
Notification from Mattress Firm Hicksville Distribution Center for today of Leon. Our delivery team is on the way.
Okay. So a solution to the homogeneous equation is e to the minus a of x, b e to the minus a of x. What is that? That's b e to the minus log of sine x, which is 1 over b, which is b over sine of x. What is the integral of q of t e to the minus a of t dt? That's the integral of 1 over sine x, 1 over sine t, e to the minus a of t sine t dt. So whenever there's a problem with a lot of calculation, I always like to double check everything. So y prime plus p of xy equal q of x. When you look for a solution of the homogeneous equation, if q of x were 0, it's e to the minus a of x, where a of x is the integral of p of t dt. So in this case, my p of t is the cotangent. So a of x is the integral of the cotangent cosine t over sine t dt. That's the log of the sine. When you differentiate log of the sine, You get 1 over sine times the cosine. So e to the minus a of x is 1 over sine of x. So b e to the minus a of x is b over sine of x. The integral of q of t e to the a of t, e to the minus a of t. So my q of t is the right-hand side. The right-hand side is 1 over sine t. E to the minus a of t is 1 over sine t. So this looks like the integral of 1 over sine squared t dt. Which is also the integral of the cosecant squared of t dt. What is the integral of the cosecant squared? Anyone remember from Calc 1? Let's see. If you were to take y equal the cotangent of x, which is cosine x over sine x, then dy dx, by the quotient rule, you get a sine squared x in the denominator, the derivative of the numerator, which is minus the sine, times the denominator, minus the numerator times the derivative of the denominator, which is the derivative of the sines, the cosine, you get minus 1 over sine squared x. That's minus cosecant squared x. So it looks like this is minus b times the cotangent. Okay. So e to the minus a of x times this integral, e to the minus a of x is b over sine x. The integral is 1 over the cosecant squared. Sorry, the integral is the cosecant squared. That's 1 over minus 1 over sine squared x. That looks like minus b over sine cubed x. Right? I think I'm off by something, but let's just write down what we have. So the general solution of the non-homogeneous first order linear differential equation is, oops, I did something wrong. What did I do wrong? No, that's right. So f of x is equal to b e to the minus ax, b over sine x, plus e to the minus ax times this. The only thing I don't like is, let's see. This is my differential equation. Y prime plus the cotangent times y equals the cosecant. So P of x is the cotangent. Q of x is the cosecant. If I integrate e to the minus ax, e to the minus ax is the log of the sine. E to that is sine, so I get 1 over the sine or the cosecant. So This is b over the sine of x. I don't know why there's a b here. Get rid of that. The integral of q of t e to the minus a of t. Q of t is the cosecant, that's 1 over the sine. Times 1 over the sine, that's 1 over sine squared, which is the cosecant squared. The derivative of the cotangent is minus the cosecant squared. So this is minus cotangent x. So e to the minus a of x, there's is minus 1 over sine cubed x. So f of x is b over sine x plus e to the minus 1 over sine cubed. Right, so I'm a little bit suspicious about this, but does anyone have a question about any of the steps I did so far? Right. Let me check everything from the beginning. So page 311, number 6. Y prime sine x plus y cosine x equals 1, or y prime plus cosine x over sine x times y is 1 over sine x. So my function p of x is cosine x over sine x, or cotangent x. The function q of x is 1 over sine x, or the cosecant of x. We let a of x be the integral, some constant times the integral of p of t dt. That's the integral of cotangent of x, cotangent of t dt. That's the log of the sine of x. Sine of x is positive from 0 to pi, so we don't even need an absolute value sign here. The derivative of the log of the sine is the cotangent. So e to the minus a of x is e to minus times the log of the sine of x minus, that's 1 over the sine of x. The integral of q of t e to the minus at dt from a to x. This is the integral of cosecant of x times cosecant of x, cosecant t dt. This is minus the cotangent of x, which is minus cosine x over sine x. So e to the minus a of x, integral from a to x, q of t e to the minus a of t dt is 1 over the sine of x, that's e to the minus ax, times this integral, which is minus cosine x over sine x, which is minus cosine x over sine squared x. So our general solution for the equation is b of x is some constant, I'll just use c, e to the minus ax c over sine x minus cosine x over sine squared x. And I'm a little bit suspicious about all of this, so let's just double check everything. Suppose I take the function y equals c over the sine of x. So dy dx, when I differentiate 1 over the sine, which is the cosecant of x, the derivative of the cosecant is what? Cotangent times cosecant. Or if we did it as follows, sine x to the minus 1, c minus sine x to the minus 2 times the cosine of x minus c cosine x over sine squared x, which is minus c cosine x over sine x 1 over sine x. That's minus c times cotangent x cosecant x. So y prime, well, let me just write it as it was. So minus c cosine x over sine squared x. So y prime times sine of x is minus c cosine x over sine x minus c over sine x, that's minus cosine x times y. So y prime sine x plus y cosine x equals 0. So we know that we've done the first part correctly. Y equals c over sine x is the solution of the homogeneous equation. Y prime sine x plus y cosine x equals 0. Okay. But I'm suspicious about my second term. Let's see. I know I made a mistake, so I just wasn't looking. This is q of t e to the at. Q of t e to the plus at. What is q of t? Q of t is cosecant. E to the at, e to the a of x, is sine of x, not 1 over it. So this is cosecant t sine t dt. Let me do this again on this page. So a of x is the log of the sine of x. E to the a of x is e to the log of sine x is sine x. So the integral of q of t e to the at, that's the integral to x. What is q of t? Q of t is the cosecant, is 1 over sine t. What is e to the a of t? Sine t dt. That's the integral of 1 dt, which is x. Good, that's better. So our general solution is y equals some constant e to the minus a of x. Let me just write it. Constant e to the minus, I'm just going to write down the general formula, plus e to the minus a of x, the integral to x of q of t e to the a of t dt. This is e to the minus a of x is 1 over the sine, c over sine x, plus e to the minus a of x, that's 1 over sine x, and this integral is x. So we get c plus x over sine x. That is, I believe now correctly, the general solution to the differential equation. I always like to check everything, so let's check. So if this is equal to y, what is y prime? By the quotient rule, we get a sine squared x in the denominator, the derivative of the numerator, which is 1, times the denominator, minus the numerator, times the derivative of the denominator, which is cosine x. So this is equal to sine x over sine squared x, that's 1 over sine x, minus c plus x, I have a minus, cosine x, c plus x over sine squared x. Let me just make this c plus x. So this is cosine over sine times 1 over the sine. So this is minus cosine x over sine x times c plus x over sine x. So y prime equals 1 over sine x minus cosine x over sine x, and this is y. So y prime plus cosine x over sine x y equals 1 over sine x, or sine x y prime plus y times cosine x equals 1. So the checks. The general solution of the differential equation is this. So success at last. Prove that exactly one of these solutions has a finite limit as x goes to 0. Well, the limit as x goes to 0 of c plus x over sine x is what? Well, as x goes to 0, this is c over sine x plus x over sine x. As x goes to 0, if c is different from 0, this would go to infinity. If c is different from 0, and this goes to 1. So the only time that, so the limit of c plus x over sine x as x goes to 0, this has a finite limit if and only if c is 0. And in that case, the limit is 1. What about as x goes to pi? The limit of c plus x over sine x as x goes to pi, So when does that have a finite limit? the denominator is going to 0, the numerator is only going to 0 if c is different from pi. So if c plus pi is not equal to 0, the limit is infinite. This goes to c plus pi, this goes to 0. So the only way this limit can be finite is if c is equal to pi, if c is equal to minus pi. And what is the limit of x minus pi over sine x as x goes to pi? Well, by L'Hopital's rule, this is the limit as x goes to pi, the derivatives, 1 over the cosine of x. As x goes to pi, cosine x goes to minus 1. So the solution of this differential equation has a limit as x goes to 0 if and only if c is 0 and we have x over sine x. And we have a limit as x goes to pi if and only if c is equal to minus pi. So this is x minus pi over sine x. Yep. Anyway, that's the solution. Takes some work, I guess. Questions about this? I mean, the problem is that when you start taking 400 level math classes, you've gotten to the point where you really need to know calculus. Okay? All right. So we've been looking at second order, linear, ordinary differential equations with constant coefficients. And the homogeneous equation looks like y double prime plus ay prime plus by equals 0. And there's a formula, if you like, we derived it, for the solution of such an equation. We let d be the discriminant, a squared minus 4b, and there are three possibilities. This can be positive, negative, or 0. So if d equals 0, the two fundamental solutions are, well, so in general, the solution is going to be y equals e to the minus a over 2x. This is a, times a linear combination of two functions, c1 times u1 of x and c2 times u2 of x. And these functions u1 and u2 depend on the discriminant, whether the discriminant is positive, negative, or 0. In the case of 0, it's very easy. u1 of x is 1, and u2 of x is 2. If d is positive, then we have solutions which are exponential. u1 is e to the kx, and u2 is e to the minus kx, where k is equal to 1/2 the square root of the discriminant. Discriminant's positive, so we can take the square root. If d is negative, then u1 of x is sines and cosines. Cosine kx, and u2 is sine of kx, where k is, so d is negative, so minus d is positive, so we can take the square root of minus d and divide by 2. So this is the solution of this is the rule for solving a homogeneous linear equation. Right? And the homework problems on page 328, they were the ones that were due last week. Maybe I'll do one just for fun. So this is on page 328, number 11. So number 11 is 2y double prime. Actually, I think I did that one, so maybe I'll do a different one. 11, 13, and 14. Let me do 14. I don't remember if I did that. So number 14 is y double prime plus 4y plus 5y equals 0. Let's make it easier to read. Y double prime plus 4y plus 5y equals 0, with the initial condition that y prime equals y double prime, and y equals 0. And y is equal to 2 when y equals 0. So at x equals 0, the function is equal to 2, and the first and the second derivatives are equal. Okay? Any questions about this? Okay, so in this case, a is equal to 4, b is equal to 5, d, which is a squared minus 4b, is 16 minus 20 is minus 4, which is a negative number. So k, which is a half square root of minus d, is a half the square root of 4, which is 1. So in the case when the discriminant is negative, the general solutions involve the cosine and the sine. So the general solution is y equals e to the minus a over 2. A is 4. A over 2 is 2. So e to the minus 2x times c1 cosine x plus c2 sine x. Okay. Let's just call this function f of x, makes it easier. And of course, from the initial condition, f of 0, when you plug in x equals 0, this is 0, c1 plus 0. c1 is equal to 2. So we know that c1 is equal to 2. Now, what about y prime equals y double prime? So we have to differentiate. When you differentiate, you get minus 2. Oops. Might need another piece of paper because this is going to be a longer calculation. We'll see if it squeezes in. F prime of x is minus 2 e to the minus 2x, c1 cosine x plus c2 sine x, plus e to the minus 2x times the derivative of this, which is minus c1 sine x plus c2 cosine x. So that's equal to e to the minus 2x. I can factor that out. And for cosine x, I have a c2 minus 2c1. c2 minus 2c1 cosine x. And for my sine x, I have minus c1 minus 2c2, so minus c1 plus 2c2 sine x. So I have f prime of x is e to the minus 2x. c1 is equal to 2, so this is just c2 minus 4 cosine x minus 2 plus 2c2 sine x. If I take the second derivative, I get minus 2 e to the minus 2x times this, c2 minus 4 cosine x minus 2 plus 2c2 sine x plus e to the minus 2x times the derivative of this, which is minus this, that makes it 4 minus c2 sine x minus 2 plus 2c2 cosine x. Now, if I evaluate this at 0, f prime at 0, this is e to the 0 is 1, sine is 0, I get c2 minus 4. And if I evaluate the second derivative at 0, I get minus 2 c2 minus 4. This is 0, plus 1 times this, plus another minus 2 plus c2. So minus 2c2 plus 8, minus 4 minus 2c2. This is 4 minus 4c2. So f prime of 0 equals f double prime of 0, means c2 minus 4 is 4 minus 4c2, which means 5c2 equals 8. So c2 equals 5/8. Okay, well, I'm always suspicious about arithmetical mistakes, so I always like to go back and check and double check. So let's go back. So here's my differential equation. Let me just make sure I wrote it down right. Y double prime plus 4y prime plus 5y equals 0. So a is 4, b is 5, a squared is 16 minus 4b minus 20 is negative 4. It's negative. And so k is the square root of 4, which is 2 over 2 So k is 1. So the general solution is f of x is e to the minus 2x. A over 2 is minus 2. C1 cosine x plus C2 sine x. And we're told that f of 0 is 2. When you plug in x equals 0, you get 1 times C1 equals 2. C1 is equal to 2. Okay, then f prime equals f double prime. So if we differentiate this, we get minus 2e to the minus 2x times this, plus e to the minus 2x minus c sine 2x plus c2 cosine 2x. Sorry, plus c2 cosine x. So f prime at 0 is equal to minus 2 c1 is minus 4, 0, 0, plus c2. Yep. F prime of 0 is c2 minus 4. We differentiate this a second time. Let me just check that this is correct. I have cosine x times c2 minus 2c1, which is c2 minus 4. And sine of 2x, I have minus 2c2 minus 2. Minus 2c2 minus 2. Okay, so this is good. When I differentiate this, I get minus 2e to the minus 2x times what we have, plus e to the minus 2x times the derivative of this, which is minus the sine, 4 minus c2, minus this. And when you plug in x equals 0, I get minus 2 times c2 minus 4, plus minus 2 little mistake here, minus, there's no 2 here, minus 2 plus 2c2. So this is equal to minus 2c2 minus 2c2 minus 4c2 plus 8 minus 2, so minus 4c2 plus 6. So this is almost right, except this should have been a 6 here. So c2 minus 4 is 6 minus 4c2. 5c2 equals 10. c2 is also equal to 2. So the solution of the differential equation that satisfies the initial condition, c1 and c2 are both equal to 2. So it's 2 e to the minus 2x cosine x plus sine x. That's the solution. Okay. Very quiet. So, well, some things are a little bit complicated to do. Okay. Any questions about this? By the way, to help you with the homework, you should all have gotten an email with the solutions to all of the problems in this ordinary differential equations chapter. And so that really is useful. Of course, you should work the problem and look at the answer. And if you got something different, do it again. Work it through, and really over and over and over again until you figure out what to do to get it right. I mean, it does take some time. All right, so this says we now know how to solve every linear second order ordinary differential equation with constant coefficients that's homogeneous. And we have to deal next with the inhomogeneous case. Or I think the book calls it non-homogeneous. Two words are used interchangeably. So we have a differential equation y double prime plus ay prime plus by equals r. So this right-hand side is some function. And if C1 V1 of x plus C2 V2 C2 V2 of x is the general solution of the homogeneous equation, and if y1 of x is a particular solution of the non-homogeneous equation, then the general solution of y double prime plus ay prime plus by equals r is y equals C1 V1 of x plus C2 V2 of x plus y1 of x. So in order to find the general solution of the non-homogeneous equation, you have to know how to find the general solution of the homogeneous equation and one particular solution of the inhomogeneous equation. So there's a general formula involving the Wronskian that I worked out last week, but there are two special cases when to find the particular solution is much easier. So you might call this tricks for two special cases. And the first case is when R is a polynomial in X. And in that case, it's enough to look for a solution of the non-homogeneous equation, which is also a polynomial in X. And we can say more than that. We can say what the degree will be. So if R is a polynomial in X of degree, what? Let me see what notation we use. Of degree n. So x to the n is the highest power of x that occurs in the polynomial. So b, if b is not 0, try a solution which is polynomial of the same degree. If b equals 0, but a is not equal to 0, then take a polynomial of degree n plus 1. And if A and B are both equal to 0, then we have an equation y double prime equals R, and we try a solution, which is a polynomial of degree n plus 1, n plus 2, 1 higher. So let's look at some simple cases. Suppose we take the polynomial y double prime minus y equals x. So in this case, A is 0, B is minus 1, right? Because it's, and R is x, which is a polynomial of degree 1. So the general theory says, let y1 of x be a polynomial of degree 1, ax plus capital AX plus b. And let's use the differential equation to try and find the coefficients capital A and capital B. So if this is y1, y1 prime is A, and y1 double prime is 0. So when you plug into this formula, what do you get? You get 0 minus ax plus b equals x, or minus ax minus b equals x. So A is minus 1, B is 0. So we have a particular solution, y1 of x equals minus x. So this is a particular solution of the non-homogeneous equation. What's the general solution of the homogeneous equation? Y double prime minus y equals 0. Well, we know that the general solution is C1 e to the x plus C2 e to the minus x minus, plus this particular solution, minus x. So this is the general solution to this non-homogeneous equation. Suppose we had, so this is on page 333, number 1. What is number 2? That's the equation y double prime minus y prime equals x squared. So this polynomial has degree n equal 2. And in this differential equation, A is minus 1, but B is 0. When B is 0 and A is non-zero, you look for a solution, a particular solution of degree 1 greater than the degree of the right-hand side. So we want to look for a solution y1, which is going to be cubic, 2 plus 1, ax cubed plus bx squared plus cx plus d. In that case, what's the first derivative? It is 3ax squared plus 2bx plus c. What is the second derivative? 6ax plus 2b. So the equation y double prime minus y prime, this minus this, is minus 6, y double prime is 6ax plus 2b minus y1 prime 3ax squared minus 2bx minus c. So if you put all that together, that's minus 3ax squared plus 6a minus 2bx plus 2b minus c. And that's all supposed to equal x squared. So if you look at these coefficients, this has to be 1, this has to be 0, and this has to be 0. Let me just double check that I did everything correctly. Y double prime minus y prime equals x squared. This has degree 2, but b is 0, so I look for a cubic polynomial that's a solution. Here's my general cubic polynomial. Differentiate 3a x squared, 2bx plus c. Differentiate again, 6a plus 2b. So y1 double prime minus y1 prime, 6ax plus 2b minus this. So I get minus 3ax squared. So minus 3ax minus 3a equals 1. So a has to be minus a third. 6a minus 2b is 0. So 6a minus 2b, 6a is minus 2 minus 2b equals 0. So b has to be minus 1. And 2b minus c, which is minus 2 minus c, is 0. So c has to be 2. So a particular solution is y1 of x equals minus the third x cubed minus x squared plus 2x, yeah, plus 2x. So that should be a solution. Let's check.
I had a question.
Yeah, go ahead.
Why are those parts equal to 0 again in the parentheses? Can you just repeat?
Yes.
6a
So
minus b of
a differential equation is y double prime minus y prime equals x squared. So if I try a cubic polynomial, ax cubed plus bx squared plus cx plus d, this is the first derivative, this is the second derivative. So when I plug these into the equation, I get y double prime minus y prime, right? So this is y double prime minus y prime, which is this. I collect the terms, but it's all equal to x squared. So two polynomials are equal precisely when they have exactly the same coefficients. So the coefficient of x squared is 1, so minus 3a is 1. The coefficient of x in the constant term is 0. So this has to be 0, and this has to be 0. So this says that a is minus a third. So 6a is minus 2 minus 2b is 0. So that says that b has to be minus 1. And 2b minus c is 0. So c is equal to 2b. So c should be minus 2. So let's just check. If I let y1 of x be equal to minus third x cubed minus x squared minus 2x, y1 prime, when I differentiate, I get minus a third times 3 minus x squared minus 2x minus 2. I differentiate a second time, I get minus 2x minus 2. y1 double prime minus y1 prime is minus 2x minus 2 minus x squared minus 2x minus 2. So that's minus 2x minus 2 plus x squared plus 2x plus 2. These cancel, I get x squared. So this really is a solution to this non-homogeneous differential equation. That's a particular solution.
So,
So I'm not done, but this is a particular solution.
what is the name of the method to solve that equation? The name?
Well, it doesn't have a name. It's in the section 8.16 in the book, which is special methods for determining a particular solution. So this is just a special method in the case when the right-hand side is a polynomial. To find the general solution, I need to find the general solution of the homogeneous equation, y double prime minus y prime equals 0. So this is of the form y double prime plus ay prime plus b equals 0. A is minus 1 and b is 0. So the discriminant a squared minus 4b is 1, which is positive. K is a half the square root of d, which is a half. So our general solution of this homogeneous equation is e to the minus kx, e to the minus x over 2, c1. So what is the solution of this? E to the k over 2 x, k over 2, sorry, e to the kx, that's e to the half x. C1 e to the x plus C2 e to the minus x. So when I multiply, I get C1 e to the x over 2 plus C2 e to the minus 3x over 2. So the general solution, the answer to the problem is y of x is C1 e to the x over 2 plus C2 e to the minus 3x over 2 plus my polynomial minus 1/3 x cubed minus x squared minus 2x.
Professor, the first step is to compare degrees.
Yeah, sorry, there's just one little mistake here. Let me just double check what I did. So, k, what is k? K is a half. This should have been x over 2. So when I multiply it out, I get C1 plus e to the minus x. C1 plus C2 e to the minus x. So this is C1 plus C2 e to the minus x. So that's the general solution to the non-homogeneous equation. Okay. So this
what
is
the reason?
sorry?
So, what is the reason you compare to 0 after the first step to get your general solution?
I'm sorry. I didn't. What is the reason I have a 0 somewhere?
Yeah, the final step to find the general solution.
Oh, well,
You
because this is the homogeneous equation. Y double prime minus Y prime equals 0. In general, a homogeneous second order equation with constant coefficients, you write it as Y double prime plus AY prime plus B equals 0. Here, the coefficient of Y prime is -1, and there's no Y. It's like B is equal to plus BY equals 0. The coefficient of Y in this equation is 0. So this says A is -1, B is 0. B is the coefficient of Y in the homogeneous equation. And the coefficient of Y is 0. You don't see it.
so from I'm referred to the square, the power of, I mean, from the beginning, right? The exercise is equal to x squared. So right now you're using 0 to find the general solution.
Well, it's not that I'm using 0. There's no 0. You have to find a particular solution to the non-homogeneous equation, and then the general solution of the homogeneous equation. So the homogeneous equation is the equation with the 0 on the right-hand side. That's the definition of a homogeneous equation. The right-hand side is 0. And the general theory of the second order equation is the general solution of the non-homogeneous equation is equal to a particular solution of the non-homogeneous equation plus the general solution to the homogeneous equation. The original equation, the problem we're solving, is this. The right-hand side is x squared, not homogeneous. But then you have to set the right-hand side equal to 0 and also find the general solution of the homogeneous equation. That's what's involved. So this is one of two special cases for dealing with the non-homogeneous equation. The second case is when the right-hand side is an exponential function times a polynomial. So the second special case is when your equation y double prime plus ay prime plus by equals r of x. R of x is a polynomial times an exponential. Okay? And there's a method to deal with this, which is the following. So we have y double prime plus ay prime plus by equals p of x e to the mx. And we make a substitution. We're supposed to let y be some function u of x times e to the mx. We're going to look for a solution of this differential equation we can write in this form. If y is u times e to the mx, y prime is u prime of x e to the mx plus m u of x e to the mx. And we differentiate again, we get u double prime of x e to the mx plus m u prime of x e to the mx. We differentiate this, we get m u prime of x e to the mx, so we have two of these, plus m squared u of x e to the mx. We can factor out an e to the mx from this. And when we do, what we get is the following. E to the mx times u double prime of x plus 2m u prime of x plus m squared u of x e to the mx. So what is y double prime plus ay prime plus by equal to? It's e to the mx times this. Plus ay prime. This is y prime. E to the mx times a u prime of x plus m u of x. So it's plus e to the mx times a times this. So it looks like I get an a squared u prime of x plus am u of x plus by, so e to the mx b u of x. So when I just put this together, this is e to the mx times what? U double prime plus, let's see, why do I have an a squared there? There's no a. E to the mx u prime of x. So u double prime plus 2m oh, sorry. Now here I have an a. This is ay prime. So 2m plus a u prime plus m squared plus am plus b u equals p of x e to the mx. And I can cancel my e to the mx's. So u is a solution of the differential equation u double prime plus 2m plus a u prime plus m squared plus am plus b u equals a polynomial. So I've just reduced this to the case where I have a second order linear ordinary differential equation with constant coefficients, non-homogeneous, and equal to some polynomial on the right-hand side. So let's look at an example. So I have the differential equation y double prime plus y equals x e to the 3x. So in this case, a is 0 and b is 1, right? Because this is y double prime plus ay prime plus by. So equals y double prime plus y. So b is 0, a is 0, and b is 1. On the right-hand side, my polynomial p of x is equal to x, and e to the mx, e to the 3x, m is 3. So if I'm looking at this in the form y double prime plus ay prime plus by equals p of x e to the mx, when my equation is y double prime plus y equals x e to the 3x, a is 0, b is 1, p of x is x, m is 3. And I'm going to look for a solution where u e to the 3x, where u satisfies this equation. What is this equation? U double prime 2m plus a is 6 u prime. M squared plus am plus b, 9 plus 0 plus 1 is 10 u equals x. So I have to solve this equation, but this is a polynomial. I can let u be ax plus b. So u prime is a and u double prime is 0. So u double prime plus 6u prime plus 10u is 0 plus 6a plus 10 ax plus b. This is equal to 10ax plus 10b plus 6. That's all supposed to equal x. So 10a equals 1. So a is a 10th. And $10b plus 6a which is 10b plus 6 over 10 equals 0. So 10b equals minus 3/5, or b is minus 3 over 50. So u1, so u of x is equal to 1/10 x minus 3 over 50, or if you like a common denominator, 5x minus 3 over 50. So a particular solution is y1 of x equals e to the 3x times 5x minus 3 over 50. Well, let me just note attendance while you are enjoying that. Let's see who is here. Amal is here. Gafour, Cabrera, Milenko, Chavez, Yapur, Lee, De Leon, Polanco, yep, I got everybody. Okay, so in the book, this is section 816. So we're looking at 815 and 816, solving these non-homogeneous linear equations with second order coefficients. And This is all basic ordinary differential equations. We'll have a few more techniques to learn. And then we're also going to do some applications, because the importance, or one of the main reasons why people study ordinary and partial differential equations, is because they're problems in physics and elsewhere that you solve by dealing with some mathematical model of your physical situation that is expressed in terms of an ordinary differential equation that you have to solve. So we will be doing some applications problems and fairly soon. Any questions about this? This is well, not supposed to be easy, I guess. Not supposed to be.
This is the two techniques. This is very new for me.
Yes. So these were the two special techniques for the non-homogeneous equation. When the right-hand side was equal to a polynomial, and when the right-hand side is equal to an exponential function times a polynomial. Yeah. Okay. That's all for today. Be back on Wednesday.
Professor, the last question. Why instead of use the natural log versus, because the
I
natural
only
log,
use the natural log. Any log, when I write LOG, this is the natural log. You don't use any other logarithm in mathematics. In calculus, they use ln for the natural log. But once you're beyond calculus, it's up to, you can use whatever you want. You can use whatever notation you want, but it always means the natural log. I usually write log.
because the natural log is the log of base e.
Always, yes.
Right.
That's the only logarithm we use.
Thank you, Professor.
Okay. All right. Be back on Wednesday. Bye, everybody.
Thank you.
It's always okay to
Bye,
turn
take
homework
care.
in late. Yes.